Here is something that should keep you up at night. The laws of physics do not care which direction time flows. Every single equation that governs the behavior of particles, every fundamental interaction, every force in nature, they all work perfectly well whether time runs forward or backward. Film a ball bouncing. Play it in reverse. Both versions obey Newton's laws flawlessly. So why then does your coffee cool down but never spontaneously heat up? Why do eggs break but never unscramble? Why do you remember yesterday but not tomorrow? The universe appears to have a deep, unwavering commitment to causality. Causes must come before effects. The past determines the future, never the other way around. But here's the paradox that haunted physics for over a century. According to the fundamental laws, there is absolutely no reason this has to be true. Causality, as you understand it, should be violated constantly. The mathematics says so, and yet, it is not. Richard Feynman, perhaps the greatest intuitive physicist since Einstein, found a way to resolve this contradiction. And his solution is not just clever, it is profound. It reveals something extraordinary about the nature of time, reality, and even what it means for something to exist. The answer will force you to question everything you think you know about before and after. About cause and effect. About the very fabric of what we call now. Jace. Let us begin. Think about causality for a moment. Really think about it. You push a glass off a table. It falls. It shatters. The pushing came first. The shattering came second. No, this feels so obvious, so fundamental, that questioning it seems almost absurd. But physics is in the business of questioning the obvious. Wow. In the late 1800s, Ludwig Boltzmann was wrestling with a problem. He had developed statistical mechanics, a way of understanding heat and entropy in terms of atoms bouncing around. His equations predicted that disorder, entropy, would increase over time. Spilled milk spreads out. Hot things cool down. Order becomes chaos. But when Boltzmann looked at the underlying equations governing individual atoms, he found something disturbing. Those equations were completely symmetric in time. An atom collision looks exactly the same played forward or backward. Nothing in the microscopic laws picked out a preferred direction. So where did the arrow of time come from? This became known as the reversibility paradox, and it tormented physicists for generations. Then came quantum mechanics. Wow. And the situation got stranger. In quantum theory, particles do not have definite properties until they are measured. They exist in superpositions, smeared across multiple possibilities. When you measure them, they collapse into a definite state. But here's the question that nobody could answer satisfactorily. What causes the collapse? When does it happen? And in which direction does the causal arrow point? Some interpretations suggested that the future measurement somehow affects the past behavior of the particle, that the effect reaches backward in time to determine the cause. This sounds like madness. It sounds like science fiction. But Richard Feynman took it seriously. And what he discovered changed our understanding of causality forever. Let us start with something that seems simple, but is not. What is time? Most people think of time as a river flowing from past to future, carrying us along whether we like it or not. The past is fixed, the present is now, the future is open. This is intuitive. This is how we experience existence. But physics tells a different story. In Einstein's relativity, time is not a river. It is a dimension, like height, or width, or depth. The universe does not have a now that moves. Instead, all moments exist together in what physicists call the block universe, a four-dimensional structure where past, present, and future are equally real. Stop. Think about that for a moment. If all moments exist simultaneously, then what is the flow of time? What is causality? Feynman understood something crucial. The flow we perceive is not a property of time itself. It is a property of causal chains moving through time. Imagine a river. The water flows downstream, from source to sea. You, standing on the bank, see the water moving. You naturally say time flows like the river. But the river does not care about time. The water flows because of gravity. because of the terrain, because of physical forces acting on each molecule. The flowing is in the water, not in some abstract property of the riverbank. Causality works the same way. Events are connected not because time pushes them along, but because physical interactions link them together. One event influences another, which influences another, creating chains of cause and effect that happen to move in a particular direction through the time coordinates. And here is where Feynman made his first breakthrough. Those causal chains do not have to go forward in time. Now, you might be thinking, wait, that contradicts everything we observe. If causes can come after effects, why do we never see it happen? Patience. We are getting there. But first, we need to understand what Feynman discovered about particles. In the 1940s, Feynman developed a revolutionary way of calculating particle interactions. He invented what we now call Feynman diagrams, pictorial representations of particles interacting, scattering, creating and annihilating each other. In these diagrams, something remarkable emerged. Antimatter. Like positrons, the antiparticle of the electron could be understood as ordinary matter traveling backward in time. This was not just a mathematical trick, it was a profound insight. When you see an electron-positron pair annihilate, producing photons, Feynman realized you could equally describe this as a single electron traveling forward in time, then turning around and traveling backward. The positron is not a separate particle. It is the same electron, retracing its steps through the time dimension. Then mathematics works perfectly. Every prediction comes out correct, and the implications are staggering. Feynman was saying that at the fundamental level, particles routinely travel backward in time. This is not speculation. It is built into the structure of quantum field theory, the most accurate scientific theory humans have ever created. But if particles can travel backward in time, why does causality never appear violated? Here is the key insight, and it is subtle, so pay attention. What we call causality is not about the direction things move through time. It is about what information can be transmitted. It is about what can be known. When an electron turns around in time to become a positron, no information travels backward. No signal can be sent. No message can be received before it was sent. The backward-moving particle is not carrying usable information from the future to the past. It is simply a way of describing the same physical process from a different mathematical perspective. Think of it like this. Imagine watching a movie of a ball bouncing. Now imagine watching the same movie in reverse. The physics looks identical either way, but in neither case can the ball carry a message backward. The information about the ball's trajectory is contained in the entire movie, not in any single frame. Particles in quantum field theory are like this. Their full story spans time in both directions. But the story as a whole respects causality. No piece of information ever arrives before it was sent. Feynman called this the principle of consistent histories. The universe allows all sorts of strange time bending at the microscopic level, as long as the overall history remains self-consistent. No paradoxes, no contradictions, just a deeper, more flexible reality than we ever imagined. But Feynman went even further. Before he invented his famous diagrams, he worked with his mentor, John Wheeler, on something even more radical, the Wheeler-Feynman absorber theory. They asked a simple question with explosive implications. When a charged particle accelerates, it emits electromagnetic radiation. Light, radio waves, whatever. That radiation spreads outward, eventually being absorbed by other particles somewhere else in the universe. Standard physics says the radiation travels forward in time, from emitter to absorber. But Wheeler and Feynman noticed that Maxwell's equations, the equations governing electromagnetism, have solutions going both directions. There are retarded waves that travel forward in time, and advanced waves that travel backward. Physicists had always thrown away the advanced solutions as unphysical. Wheeler and Feynman asked, what if we keep them? What they discovered was astonishing. If you allow both forward and backward waves, something beautiful happens. When a particle emits radiation, it sends out waves in both temporal directions. The forward wave heads toward the future absorber. The backward wave heads toward the past. But here's the key. The future absorber also responds. It absorbs the forward wave and re-emits its own waves, including backward waves that travel back toward the original emitter. These backward waves from the absorber arrive at the emitter at exactly the moment of emission. They combine with the original forward wave in just the right way to produce what we actually observe. Radiation traveling forward in time, with no apparent backward component. The backward in time waves cancel out at the moment of emission. They leave no trace, but they are essential for the mathematics to work. Think about what this means. When a light bulb turns on, electromagnetic waves spread outward. But according to Wheeler and Feynman, those waves are not just going outward. They are being met simultaneously by waves traveling backward from every future absorber in the universe. The absorbers in the future are participating in the emission in the past. The handshake happens across time. This is not mysticism. This is physics. Mathematics checks out. And while the absorber theory was eventually superseded by quantum electrodynamics, the conceptual framework remains valid and has been extended by others into full quantum mechanical interpretations. Now you might be asking, if all this backward in time physics is happening, why do we never experience it? Why does the world appear so stubbornly one-directional? The answer lies in statistics and boundary conditions. Remember Boltzmann's paradox? The microscopic laws are time-symmetric, but macroscopic behavior has a clear arrow of time. Feynman understood that this asymmetry does not come from the laws. It comes from the initial conditions of the universe. Here is an analogy. Imagine you shuffle a deck of cards. The laws of shuffling are symmetric. Any arrangement can lead to any other arrangement with enough shuffles. But if you start with a perfectly ordered deck, ace through king in each suit, then any shuffling will make it more disordered. The disorder does not come from an asymmetry in the shuffling rules. It comes from starting in an unusually ordered state. The universe is the same way. The Big Bang was an extraordinarily low entropy state. Everything was smooth, uniform, tightly packed. From that special starting point, the laws of physics predict that entropy will increase, disorder will grow, and time will appear to flow in one direction. But the laws themselves do not care about direction. A universe that started in a high entropy state would evolve backward, becoming more ordered over time, and any creatures in it would experience causality in the opposite direction from it. Causality is not written into the laws of physics. It is a consequence of how the universe happened to begin. Wow. This is why quantum mechanics can have particles traveling backward in time, retarded and advanced waves combining across temporal directions, and all manner of time-symmetric processes, without ever violating the causality we observe. The individual pieces can go any direction. The cosmic whole has an arrow, but it is not fundamental. It is emergent. It is a boundary condition, not a law. Now, let us go deeper still. In quantum mechanics, there is a phenomenon called entanglement. Two particles become correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance. Wow. For decades, physicists argued about how to explain entanglement without invoking faster-than-light signaling. Various interpretations were proposed. Hidden variables, many worlds, pilot waves. But there is another possibility, one that Feynman's framework makes natural. Retrocausality. What if the correlation between entangled particles is not transmitted instantaneously across space, but transmitted through time, going backward from one measurement to the common origin, then forward to the other measurement? This is a zigzag through space-time. Each segment travels at normal speeds, within the light cone, perfectly compatible with relativity. But the overall effect connects two space-like separated events without any mysterious action at a distance. Researchers have shown that if you allow this kind of retrocausality, you can construct local hidden variable theories that reproduce all the predictions of quantum mechanics. The price of eliminating spooky action is admitting that the future can influence the past. But here is the crucial point. This backward influence can never be used to create a paradox. Why not? Because of a constraint that emerges naturally from the physics. Backward causal effects cannot be known. until after their causes occur. Think about that carefully. If an event in the future causes something in the past, you cannot know about that past event until after the future cause has happened. Any attempt to measure the effect early would disrupt the backward causal process. This is exactly what we see in quantum mechanics. You can set up experiments where the outcome seems to depend on future choices, but you can never exploit this to send information backward. The statistics work out such that no paradoxes arise. The delayed choice quantum eraser is a perfect example. In this experiment, which has been performed in real laboratories, you can make it seem like a particle decides retroactively whether to go through one slit or two, based on a measurement you make after the particle has already been detected. But here is what actually happens. The interference pattern only shows up when you correlate your data with the later measurement. Looking at the data before that correlation reveals nothing. The backward influence is real, but hidden until the forward chain catches up. Quantum mechanics respects causality not by forbidding retrocausality, but by making retrocausality undetectable until it becomes normal causality again. The universe is playing a subtle game, and Feynman was one of the first to understand its rules. So where does this leave us? The laws of physics are time-symmetric. Particles can travel backward. Advanced waves from the future can reach into the past. Retrocausality may underlie quantum entanglement. And yet, causality as we experience it remains unbroken. This is not a contradiction. It is a clue. Causality is not a constraint imposed on reality from outside. It is a pattern that emerges from within. It is a consequence of how information flows through the web of events, which itself is shaped by the initial conditions of the cosmos. We live in a universe where the past and the future are both fixed, both equally real, both part of an eternal four-dimensional structure. What we call the flow of time is our experience of causal chains propagating through that structure. We remember the past because causal chains carrying information reach us from earlier times. We cannot remember the future because no causal chain has yet connected us to it. But the future is not open. It is not waiting to be determined. It is already there, in the block universe, waiting for our causal chains to reach it. This should be terrifying. It sounds like determinism, like free will is an illusion, like nothing we do matters. But Feynman did not see it that way. In Feynman's path integral formulation of quantum mechanics, a particle does not take one path from point A to point B. It takes all possible paths. Every trajectory, every crazy zigzag, every route through space and time contributes to the final outcome. Reality is not a single thread. It is a sum over histories. And you, standing here in this moment, are not a passive observer. You are an emergent property of this vast causal web. You are something new that arose from the interaction of countless paths, countless particles, countless events stretching back to the Big Bang. Your choices are part of the structure. Your actions contribute to the sum. You are not separate from causality. You are causality expressing itself through a particular pattern of matter and energy that has learned to reflect on its own existence. That is not a loss of meaning. That is a different kind of meaning altogether. The universe is not a movie playing forward, frame by frame, with you watching helplessly. It is a timeless tapestry, where every point depends on every other point, where the future shapes the past as much as the past shapes the future, where the whole exists as a self-consistent unity. And somehow, within that unity, there is you, thinking about it, asking questions. Wondering. Richard Feynman once said that the pleasure of finding things out is the reward. Not fame, not recognition, not even the utility of the knowledge. Just the joy of understanding something that was previously mysterious. What we have explored here is exactly that kind of mystery. Causality should be violated. The equations say so. But it is not violated, not in any way we can exploit or observe. The resolution is not that the equations are wrong. The resolution is that our intuitions about time are incomplete. Time does not flow. Causal chains flow through time. And those chains can go in any direction as long as the overall pattern remains self-consistent. The universe is more flexible than we imagine, more strange, more beautiful, and we are part of it. We are made of the same stuff, obeying the same laws, woven into the same causal web. There is something humbling about that, and something inspiring. Because if the universe is this subtle, this elegant, this profound, then there is always more to discover. Always deeper layers to uncover. Always another mystery waiting to be understood. Feynman knew this. It is why he spent his life chasing problems, asking questions, refusing to accept easy answers. And it is why we should do the same. The next time you see an effect and think you know its cause, pause for a moment. Consider that the cause might be in the future. Consider that the effect might reach backward. Consider that the universe is playing a game far more intricate than simple before and after. You cannot see it directly. You will never catch it happening. But it is there, hidden in the mathematics, shaping the reality you take for granted. Causality is not what you think it is. And the truth, as always, is far more beautiful than the lie. End title card. Physics explained simply. How 20 matters. Subscribe, call to action. Related videos suggestion area. Final fade. Channel logo.